Thank you very much. So I'm back for this third and last lecture, and the objective is still, before discussing in the other lectures, mostly the subject will be Anosov subgroups, and even if they are not explicitly mentioned in the title of the conference, they are still at the core of one of the main purposes of this conference. And still, they will not appear in my lectures, but the purpose of my lectures is what can you say when you have, to understand what you can say when you have a discrete subgroup of a semi-simple Lie group. What are the objects that you have, and then next, how they will play a role when you study Anosov subgroups. And yesterday, so in the first lecture, I introduced G will still be connected semi-simple Lie group, and I hope now you are not scared anymore by this object, because it's just the group, either the full linear group over R or C, or the full symplectic group over R or C, or some orthogonal group over R or C, or some Hermitian group. Anyway, it's a member of a list. So it's a very tame group. And in this group, so we have introduced the Cartan decomposition. So it appeared also in other talks. So we have a maximal compact subgroup. So the picture is that this maximal compact subgroup is some point in the symmetric space of G, and we choose a maximal flat which contains this point, and in this maximal flat we have chosen a certain cone. This maximal flat is a Euclidean space, and the Cartan decomposition tells you that any point can be moved back inside this particular cone in this maximal flat. This defines, so usually the Lie algebra is denoted by A, but it's essentially the same object, because the exponential map between small a and Gothic A and big A is a diffeomorphism, so it's essentially the same object. And we denote by kappa, not mu, the Cartan decomposition, the Cartan component, the Cartan projection, which looks at the guy in the middle. And it's a kind of vector. If the space is a group has rank 1, this is just a non-negative number. Yes, non-negative, okay, fine. And this number is just the distance. It is a distance between x and gx, where x is this point, gx is here, okay? And in general, it has to be thought of as a kind of vector distance, vector-valued distance. And today, what I will do, so yesterday we described the limit cone of Benoit, L gamma, which is the asymptotic cone of the set kappa of gamma. There is no gamma, so gamma will be a Zariski dense subgroup. And the limit cone, so inside we have this cone, A+, and we look at all the limit directions of the set kappa of gamma, and we get a convex cone with non-empty interior. And today we will start studying, we will assume moreover that gamma is discrete. So yesterday we discussed this, and we see that essentially an interesting Zariski dense subgroup is discrete. And we will study the speed. We will try to introduce objects for counting the speed with which elements go to infinity inside this cone. And so a first object, when you want to study the speed, since everything has is non-positive curvature, what you expect is for this speed to be exponential. You expect to have exponentially many points going to infinity. Okay, so you introduce your exponential rate. So it's called the exponent of growth. So I will denote it by tau because delta will be for Dirac mass. Okay, so, tau gamma is exponent of convergence of the Dirichlet series. So you have this Dirichlet series, and you look at the exponent of convergence, and this is about you can describe it. So it's the exponential rate of growth, and you can also write a formula, a Hadamard formula, that is tau gamma. So here the norms I put is just any norm for the moment. Let's say that it is the norm coming from a Riemannian metric on G mod K. A Riemannian metric on G mod K fixes a norm, a Euclidean norm on every tangent space. So I'm taking the Riemannian metric. But actually, so, yes, okay. So of course the exponent depends on the norm. So tau gamma, you can say that it is the lim sup as say a goes to infinity of 1 over a, the cardinality of the set of gammas in gamma, such that a is lower and this is true. This does not depend. This is true for any b positive. That is what I'm saying is that I'm looking at this set kappa of gamma. I'm looking at the number of guys inside such a sector, and I'm letting a go to infinity. And there is a log missing. Let's see. So I'm counting the logarithm of this number because I want to estimate the exponential behavior of the norm of kappa gamma, this number. I'm dividing by m, letting a go to infinity, and actually this number does not depend on the choice of b. As soon as you are authorized to count the number of points in a slightly thick sphere, you get the same result. It's the general properties of Dirichlet series. It's absolutely, it does not use anything. So in rank 1, this set A plus is just a half line. And basically, historically, the story stops here. That is, you are counting, you're in rank 1. You are counting in intervals A plus B. And basically, the story stops here. And in higher rank, you can ask for a more refined version of this object because you can ask what happens globally, but also you can ask what happens in a small sector. You fix a cone, and instead of counting everything, you restrict yourself to this, to what happens in a given set of directions in a small cone, okay? And you can define a restricted exponent, tau gamma c, which is the exponent of convergence of the restricted Dirichlet series, which is put an arrow, it's a vague symbol. Instead of looking at what happens everywhere, you fix a cone, and each time you fix a cone, you can look at this restricted Dirichlet series. And then what you can do is shrink the cone by letting around the vector, and you can define an object. You can do, when you have x, say you can put any x in A, but you will just get minus infinity. You can define the infimum over all cones, open cones. So I will take C to be an open cone. All open cones containing x of this exponent tau gamma c. And so for the moment, this computation depends on the norm. Okay, and but what you realize is that since everything happens only close to one direction, and since all norms are locally proportional, okay, actually if you renormalize by the norm in this way, the result of this computation actually does not depend on the norm. Okay, so small exercise. And this, you call it psi gamma of x. It's a function of x. And this function counts, estimates the exponential behavior of the set kappa of gamma in any direction. Okay? And does not depend on us. It's a kind of invariance. So psi gamma, it's a homogeneous function. 40 positive. And it's just because it's defined as some infimum of something, it's also it's upper semi-continuous. And I should say, it's also psi gamma x. It has to be thought of as an element of minus infinity. Infinity. So it's everywhere finite because the exponential, we saw estimates of the volume of this kind of sets in some talk yesterday. So this set is the volume for the R measure, okay? They grow exponentially. So since your group is discrete, the number of points is bounded by the term for the R measure. So we know that this is finite, okay? Just because by the formula for the group itself. So we know that it's finite, but if you are looking at what happens, if your limit cone is here, and you are looking at what happens far away from the limit cone, basically this number is minus infinity. Okay, that is the theory converges everywhere because it's just zero. Okay, so but it's better. So at least for me, it's better to think to it as being a function that is defined everywhere, but may take the value minus infinity. It's more comfortable for some formulas. Okay, so you can introduce, and so by the way, this is a general. So this is a general object that you can introduce as soon as you have, say, a set in some vector space, or even a measure. You can consider this kind of object. You want to estimate directional exponential behavior of some counting object in some space. So, for example, you can. This happens. So it's related. Counting this way is related to what you do in a large deviation theory, in a theory of classical random walks. So let me do a parallel. That is, if you do random walks, say on some vector space V. Okay, so you have a probability measure, and now I'm using the letter mu. And you have a probability measure. Then you can define, associated to this situation, you can define a radon measure. So mu is a probability measure on some vector space V. Okay, and you can define a radon measure on the vector space R cross V. Okay, and this radon measure is the sum for all n, an integer of the product of the Dirac mass at n with the nth convolution power of n. So what you are doing is you have your space V at time 0, then at time 1, at time 2, etc., etc. And you are looking at the measure where at time 0 you are at 0. Okay. At time 1, you are distributed with respect to the first step of the random walk. At time 2, you are distributed with respect to the second step, etc., etc. Okay. And you could do the same process. That is, you could look at now. So it's not a Dirichlet series; it's an integral. So you could look at this kind of series. Sorry. Integral over V of exponential minus T n plus S norm of V okay, so I'm looking at, this is exactly the same kind of object, but instead of working with counting measures, I'm working with random walks, okay? So you can look at this kind of integrals, and you could also restrict this kind of integrals to some cones, exactly the same way as I did, okay? And associated to this, you can build a function psi. I don't rewrite the formula, but you will get a certain function psi, which is a function from R cross V towards the same. That is, so if you towards the what? Towards minus infinity. No, how? What is, yes, and now, but now you see you have a particular decomposition. It's a homogeneous function, and it's mainly interesting in those directions because backwards you don't see anything. Okay, so essentially the good object is the object in probability theory. You study this function IV, which is I put a minus, which is minus psi of 1v. That is, you restrict your function, you normalize. Since it is a homogeneous function, you can restrict it to this vertical line, okay? And this function is called the large deviation profile. Okay, so the function I'm writing here, okay, it's a version of the function that is called the large deviation profile in probability theory. It's just the same object, except that since when you work with in large deviation theory, in probability theory, you are interested in measures having this particular form, so you don't write it exactly the same way, but it's the same kind of object, okay? And in probability theory, this function is actually a convex function. And in our case, since there is a minus here, this function psi gamma will be a concave function. So it's a theorem that when gamma is discrete and Zariski dense, psi gamma, which goes, so I prefer to write it as a function defined everywhere, even if it takes the value minus infinity. So it's a function, again, from minus infinity, infinity. And it's, so we already know that it is upper semi-continuous just because it's a ephemum of something, that it is homogeneous, but it is a concave. And also it's related, actually the cone, this convex cone that we see here is exactly the cone where the function is really defined, that is the cone where the function is not minus infinity. Okay, so the cone L gamma is exactly the set of, say, x in A, such that psi gamma of x is not minus infinity. Okay, and actually, when it is, since it is a counting measure, it's not really difficult to see that as soon as it is not minus infinity, it is non-negative. Okay, so what? And actually, I should have said that it's just from the very definition. Actually, the function psi, it allows to recover this exponent of convergence, that is tau gamma, and it's just abstract nonsense. That is, you don't have to use the fact that you have a Zariski dense subgroup, it's a general property. That tau gamma is just exactly the supremum over non-zero x's of psi gamma x divided by the norm of x. That is, the function psi gamma here, it does not depend on the choice of a norm, but when you fix a norm, you can recover. Every norm defines an exponent of divergence because you can. Every norm changes the series, and when you change a norm, you change the exponent. Okay, but actually, this function psi gamma, it contains all the information on the different exponent when you let the norm vary. Okay, so it's an object that whatever the way you want to count the exponential growth of your group, this information is contained in the data of psi gamma. And so mostly the purpose is to study groups which are not lattices in these lectures, because for lattices, all the questions you may ask, they have answers that are really clear.
But this function was introduced by you, and then this theorem is due to you. I guess.
I guess. Okay. And so do I. And
That's why they call it growth indicator function. I was always wondering why your name was.
Right, maybe the name might be good, growth indicator.
growth indicator, okay. Growth indicator.
Because you mentioned Benoit many times, you could mention Quint once, right?
No, but in Yves' talk, he will mention me.
Oh, okay.
And so, for example, a stupid example is okay, but still it's interesting to know that you can compute. If gamma is a lattice, then what is psi gamma? Psi gamma actually does not depend on gamma. It's the same for every lattice. That is because lattice fill all the space. So you have the same asymptotic behavior as the one you have of the full group somehow. And this function is a classical function that appears in representation theory. So it is equal to the sum for all non-negative roots. Okay, so we saw this set sigma plus, the set of weights of the representation of A in G, in the Lie algebra, yesterday, and you multiply by the dimension of the weight space. It's not very, if you don't care for this formula, it's not very important. If you already saw this kind of formula, this is a very classical formula of analysis only groups. That this is an object that appears several times. Okay.
So what happens at the boundary of L gamma? You still have...
That's a good question. Okay, I don't know. It depends. Okay.
But it is greater than...
For example, for lattices it is, because the boundary of L gamma is everything for lattices, and at the boundary you have this function which does not vanish. Okay? And for example, if you take... For Schottky groups,
In the interior.
it vanishes. For Schottky groups, it vanishes. For
really?
yes, so it depends.
For some Schottky group, right? Not for every Schottky group.
I don't remember. Does it vanish? No, not always.
I thought it could depend on which Schottky group.
Okay, I don't remember.
But the interior is strictly positive.
Yes. Interior is strictly positive just by concavity. Okay. Okay. Yes, you're right. I should say that. Just by, since it is concave, psi gamma, it is concave and non-zero, okay? So necessarily psi gamma is strictly positive on the interior, okay? Because if it vanishes somewhere in the interior, it is, okay, yes, I should draw a picture somewhere. You have to think, if you take a section, you have the set A plus is some interval. Inside A plus, you have L gamma, which is a smaller set, okay? And you expect a picture, I don't know, of this form, something like it, okay? And maybe it vanishes, maybe it does not. Okay, but if it vanishes everywhere, if it vanishes somewhere in the interior, and since it is not negative, you are stuck by the concavity property. And also, it turns out that when you study carefully what happens when you prove this theorem, you can say a bit about counting in general. You can prove that it is a corollary of the proof that actually. When you want to count the number of guys in a ball, this limb soup that appears somewhere, there was a limb soup, I forgot. Yes, tau gamma. It's a limb soup, so now I'm counting in thickened spheres. So when you count in balls, actually you have a true limit. That is tau gamma. It's really the limit as a goes to infinity of 1 over a, the logarithm. Of the cardinality of the set of gamma, so that's the norm of kappa of gamma. Okay, so just in this very general framework, you have already a bit of regularity. Okay, that you don't have a very strange fluctuations of this number. Okay, it's not it has a slight regularity of growth. Okay, so at the it's very logarithmic level, but still there is a slight regularity. So now the reason why this theory which I'm trying to develop for higher rank groups, it's based on a theory that was developed in the 90s, the 1990s. For rank 1 groups, where people just studied this exponent and then wanted to estimate really this number. Okay, and it is a story that surely a lot of you know that when gamma. So I'm stating a theorem. Maybe it's better to write as a theorem. So under some additional assumptions, when the rank of G is 1, so it's a theorem that I can attribute maybe to Patterson, Sullivan. Maybe I should start Tsuji at some point. And I think that this final version, I have to attribute it to Roblin. Some other people in between, but I forgot. And if the rank of G is 1, and if gamma has finite BMS measure, BMS tending, I think this measure already appeared yesterday, it's Bowen, Marguly, Sullivan. So for the moment I won't define. Hopefully, if I'm efficient enough, I will come back to this assumption before the end of the talk. But you have to put an assumption, it's false in general. So it's an important assumption. I should not put it into brackets, and I should circle it. I should circle it in red, much better. And under some additional assumption, you can prove that the cardinality of this set, and here I will rewrite the true meaning of the Cartan component in rank 1, it is really a distance. This cardinality, the number of points, so I'm looking at symmetric space, I have a starting point at, and I'm counting the number of points in the orbit inside the ball. This number is equivalent to a pure exponential multiplied by some constant, which depends on x. Okay, so you have much more than this just estimate at the asymptotic level, at the logarithm level. You really have a pure exponential behavior. Okay, and
so, yes, sorry. You said the true meaning was the distance in rank 1, but it's also true in higher rank. No?
It contains the distance. It is more precise because it's the norm. The norm of the Cartan component is the distance.
Ah, yeah, okay. Which is what you're looking at.
Yes, but I also studying in directions, etc. Okay, so. And yes, so this number, when I write the norm of kappa gamma, yes, it's distance between x and gamma x. That's true. Okay. And okay, so in rank 1, you have nice subgroups. So typically, we saw yesterday convex co-compact subgroups. So convex co-compact subgroups that fit in this assumption. Okay, and for nice families of groups, you can prove that this asymptotic behavior is just a pure exponential. And so the strategy for proving this is a strategy that could be called the Marguly Strategy. What you will do is that you will build a dynamical system. So essentially, it will be the geodesic flow. As you will have, since you will look at this quotient symmetric space. So when gamma has torsion, it's not exactly a nice quotient, but still you can think to gamma as having no torsion. There's not essential difference. And you will look at the geodesic flow of this dynamical system, and you will build a very nice invariant measure for this geodesic flow, which has a mixing property. And this counting property is a consequence, is a translation of the mixing property. And this is, so using mixing to count objects in negative curvature, negative, is a strategy that was devised in Marguly's thesis, okay, where he counted periodic orbits for geodesic flows of compact, negatively curved manifolds. And by pushing this strategy, you can reach this kind of results in this case. And one of the main features is to introduce the good measure. So the good measure with which to work, which is somehow a measure of maximal entropy. And in the remainder of this talk, what I will do is that I will try to define so there are steps for building this measure. There are several steps in rank 1, and I will define the first steps in this strategy. And maybe in the next talks, people will reach the last steps, okay? But I will start introducing the tools for building this good measure in rank 1 and how but by taking the point of view of higher rank. That some of these constructions, they can be extended to higher rank, so I will build them with no assumption on the rank. Okay? So this is so the story, okay, is that you will first, so you want to build a measure on the tangent bundle of this, and in rank 1, the unit tangent bundle of this is a space that is defined in general, okay, whatever the rank, and so it's not equivalent. So you need the tangent bundle. It's a space that was denoted this way in the talk by T yesterday, okay, and it is a quotient. You take a double quotient. Here you have this group M, which is a small compact subgroup in the centralizer of A, the compact centralizer of A. And you mod G on one side by M and on one side by gamma. Okay? And the goal is to construct the Borel-Marguly measure, which is a measure on that space. And the strategy is this flow, it has hyperbolicity properties in rank 1. So on that space, when you look locally, what you see is a picture of another of hyperbolic dynamics, such as you have the direction of the flow, say, and then you have a stable direction and an unstable direction. And we will build the measure by writing it locally as some kind of product of, you want an invariant measure. So in the direction of the flow, the measure has to be Lebesgue measure, okay? And then you will take a product of what happens in the unstable and stable direction. Okay, but since you have a lot of geometry, it turns out that you won't work locally, okay? You will use some trick of geometry to bring everything back to some other space, okay? And so first step is to say that building a measure on that space is the same as building a measure on G mod M that is gamma invariant. That this is the same, okay? So now we won't study this space, but we will study G mod M, okay, and look for gamma invariant objects, okay? And then this splitting, this local splitting that you have in mind if you are a dynamist, okay, it will be related to some decomposition of that space as a product of two spaces, okay? And so now I will study the bricks in this product. I will come back. So this decomposition is what's called Hopf's parametrization, okay? And I will first look for measure on another space which will be related to this decomposition later. And this space is the space G mod P that we encountered yesterday that appears everywhere. Okay, the space of flags. Okay? And on that space, so you can look at the action of gamma. So gamma acts on G mod P. Okay? And on that space, you don't have gamma invariant measures. Okay? So later, this problem of invariance will be dealt with when moving to G mod M, but for the moment, we don't look for gamma invariant measures. We look for measures which were quasi-invariant, okay? And quasi-invariant means that you have so in general, so I forget about this concrete situation. So my situation is that I have a group gamma acting on some compact space X, and I want to study measures which are not necessarily invariant, but quasi-invariant. What quasi-invariant means, it means a measure nu is quasi-invariant if when I push the measure by gamma, I find a measure which is equivalent to nu, where equivalent means having the same set of measure 0. And this is equivalence in the sense of the course of measure theory. Two measures are, that is, these two measures are absolutely continuous with respect to each other. And whenever you meet this situation, which is actually quite frequent, you know that you can expect a change of variable formula. That is, you can find, and this is the Lebesgue-Radon-Nikodym theorem. So what it says is that you can find a map, a function, so I'm vague about our assumptions, okay, which is a function, a positive function, which is defined nu almost everywhere in X, such that you have a change of variable formula, such that for any nice sinus function on R, when you look at the integral over X, and for any gamma in gamma, when you look at the integral of sigma of gamma X, f of gamma X, d nu of x, you recover. Okay, so this is exactly the change of variable formula. So in the classical calculus, what you get here is the absolute value of the derivative. Okay, but in general, what Lebesgue Radon-Nikodym tells you is that as soon as you have equivalence of the measures, okay, quasi-invariance of the measures, then you have a change of variable formula. Okay, and this function sigma, due to the fact that it satisfies this property, it has to satisfy the chain rule. This is the same formula as this formula of calculus when you see here the derivative or the absolute value of the Jacobian in general. And what is the chain rule? The chain rule is this formula. And you just write that if it is true for gamma 1 and gamma 2, it must be true for the product. And you have the chain rule that comes at once, which tells you that you must satisfy this property. And this property is called the one cocycle property. So it is a chain rule, or the cocycle property. So if you are a specialist of analysis, you can use the chain rule. If you are a specialist of group theory, you can use the cocycle property, but it's exactly the same relation. And so if I look, so it's kind of miracle here is that on that space, we are looking for quasi-invariant measures, but we have very nice cocycles. So what we will look for is we will fix the cocycle and trying to find the measure which satisfies the chain rule, so the change of variable formula. Okay, and why do I have one question is why this space comes with very nice cocycles? And so you have several interpretations of this. I will give you one that I like. I hope you will like it too. So again, we are provided with a gamma acting on a space. But actually, this space is a quotient of some bigger group, and gamma is a subgroup of the bigger group. So the situation now, I will not study gamma, I will study G. So I have a group, and I'm looking at its action on some quotient, and H will be P, okay? But this is just an abstract discussion. And what I'm saying is that as soon as I have a situation of this form, I have a cocycle. This always define, up to cohomology class, this always define a cocycle from G, this space I will call it X, from G cross X towards H. As soon as you have this situation, you have a cocycle. And the reason why is because you can always, at least set theoretically, you have this quotient map, G over G mod H, and you can always choose a section. Okay, so let me call pi the quotient map. And what is a section? It's a map that is the inverse of pi, so it is a map such that pi of S of X is X. That is above every point, I choose a pre-MAG. Okay, so at least that theoretically, you can always do it. And even in the Borel category, in measurable sets, there is no trouble. And if you fix a section, then when you apply G to S of X, okay, so you take a point downstairs and you push it by an element of the group. So you know that you should recover something which lies above Gx. Okay, but this something, when you start from X, you lift it, you get S of X. If you move down in G mod H, you go to G mod X, and here you will move to something. If I push G, I will move to G S of X, but G S of X is the same fiber of S of Gx. Okay? So necessarily, I must have another element here, and this sigma of Gx is some element in H. Okay? So because I'm moving to the same fiber, the projection is equivariant for the action of G. Okay? And this sigma is just, if you look at this formula, this sigma is a cocycle. Okay, so as soon as you have a group acting, and actually, so you have the notion of cocycles being homogeneous, co-homogeneous? Homogeneous? No, co-homologous, sorry, I'm tired. Co-homologous. And as soon as, if you take two different sections, you will get two cohomologous cocycles. So if each time you have a group acting on a quotient, you have a cohomology class appearing. Okay? And in our situation, so we have a cocycle.
This is just the Borel cocycle, right? It's a measure of.
There are no assumptions here. Okay. So,
I mean, this is just another way to think about a group action.
Sorry?
It's not defined everywhere. Like it's only defined.
if you choose a section, it's a set theoretic statement. I'm not putting any action. Okay, I'm just giving you a feeling. Okay. So why you can expect for cocycle formulas as soon as you have an action on the quotient. And in our situation, we can first look at the action of G on G mod AN. So we lift a bit. You remember that this is just a small compact group. In case of SLN, for example, this is just a finite compact group. So it's a small lift, okay, of the action. Now, this is a kind of sphere. Instead of projective space, you take sphere here, okay? And in this case, you have the Iwasawa decomposition. Huh? And the Iwasawa decomposition, it tells you that J is KAN. It provides you can see it as provides a section of the quotient map. Okay? I told you to build a cocycle, what I need is a quotient and a section. Okay? And in that case, the quotient is a quotient by AN, and precisely this Iwasawa decomposition tells you that you can take the section to be K. Okay? You take the unique lift of a guy here that belongs to K, which tells you that I have a section. Okay? And this section will define the first cocycle, say sigma 0, just by this formula. And it turns out that it is a better cocycle, it's better, so what? You have a lot of luck here, okay? And it's better, so I should maybe say a word on this Iwasawa decomposition first for those who are not familiar, because I did not mention it for the moment. This Iwasawa decomposition, it's always true. And in case of SLN, as usual, it's a classical property. It is a Gram-Schmidt decomposition. Okay, it's Gram-Schmidt orthogonalization process. And if you take any, again, if you take any classical group, you take symplectic group, orthogonal group, whatever, it's just a simple exercise to show that when you start with a symplectic basis and you apply to it the Gram-Schmidt orthogonalization process with respect to some nice scalar products, or some nice K, actually you end up still with a symplectic basis. And what it means is that when you take Gram-Schmidt orthogonalization process, classical groups are stable under this process. Okay? And so you can check it on examples, it's absolutely easy. Okay? It's not trouble to check it. And so, and you rewrite it as this abstract statement, and this abstract statement, today I interpret it as saying that there is a nice section, when I fix a maximal compact subgroup, there is a nice section of the quotient map. So I have the first cocycle, which goes from G cross G mod AN towards AN. And now N is a normal subgroup of AN. So I can take a further quotient and see it as a cocycle with, I can forget about the N component and see it as a cocycle with value in A. And A is the same as its Lie algebra. Okay? So actually, from Iwasawa decomposition, I have this cocycle. And now what happens is that due to the fact that when I want to go to, from the start, I want to go to G mod MAN. Okay? But here, M is actually contained in the section and commutes with A. And due to this fact, just by elementary formulas, you can see that actually, since I forgot the component in N, actually this cocycle, it will give me a cocycle of this form. Okay. Just because everything is defined in K, M is in K, and commutes with A, etc. You can mod out by M here, and this does not change the value of the cocycle. So we come up, so it's a bit abstract as a justification, but the goal is to convince you that here I have a vector-valued cocycle that goes towards A, my space A. And what happens in rank 1 is that this cocycle is the Boozman cocycle. This space A is just R, so you have a real-valued Boozman cocycle. And the construction of Patterson and then Sullivan and Patterson for SO21 and Sullivan for SON1 gives you nice measures for which with respect to this real valued cocycle, so maybe you have to take an exponential to get a positive valued cocycle, you have some nice measures appearing. So in general, we will follow their strategy. Now we have extended this Boozman cocycle as a vector-valued cocycle, so in higher rank, and given a linear functional. So we have a vector-valued cocycle, and we want to make it into a scalar-valued cocycle. So what we do is that we take a linear functional on A, and we evaluate the linear functional on the vector-valued cocycle, which will give us the scalar-valued cocycle. And we will say that new probability measure on G mod P is phi, gamma phi Patterson-Sullivan measure if the change of variable formula holds for this cocycle, if for every, say, continuous function on G mod P, when I look at the integral of over G mod P of exponential minus phi of sigma for any gamma in gamma, that is what we're looking for. Instead of looking for invariant measures, which do not exist, we fix the change of variable formula, and we ask that the measure satisfies this change of variable formula. Okay? And
I mean, wouldn't it be more consistent with the rank one if you call it gamma psi conformal measure instead of gamma psi PS measure?
No.
Because that's what kind of Sullivan called.
no, because he has this idea coming from where he looks at a field of measures, defining on G mod P. So, okay, anyway. I don't like it.
There is a gamma psi conformal, in rank one there is a gamma conformal measure of every dimension, and the Patterson-Sullivan measure usually denotes the measure supported on the limit set, like with a specific critical exponent. So
G doesn't act conformally.
Okay,
so
this is a discussion about terminology. I will move on, and I'm the speaker. So, and the theorem, which is an extension of results of Patterson and Sullivan in rank 1, is that, so I will come back to their work, and is if there exists a gamma phi Patterson-Sullivan measure, then phi is bigger than psi gamma. And this is an inequality between functions on some vector space. It's not two numbers. And if phi is bigger than psi gamma, and there exists some x inside the interior of A plus, such that phi of x is equal to psi gamma x, then, so there are 2 points. There exists a gamma phi Patterson-Sullivan measure. So it's just a direct generalization of the work of Patterson and Sullivan. The picture, maybe I should keep this, I don't know what I can, maybe I will erase this.
but in the second statement, it's very important to point out the existence of measure is on the limit set, I think.
On the limit set. You see, I'm open to negotiation. So the picture, it comes from, even if formally the fact that psi is concave does not appear in this theorem, the picture is a picture of convex geometry. So I look at what happens on a section. I have my cone A plus, and inside my cone A plus, I take a hyperplane section, okay? So I look, inside A plus, I have the limit cone, and on the limit cone, I have the function psi gamma. Okay. On that section, the picture you see is you have, say, if you are in rank 2, you see an interval, which is a limit cone, and you see some convex function. Okay. And what is a linear functional on a section? On a section, a linear functional is a fine functional. Okay. And what I'm saying is that if you have a measure, necessarily the affine functional has to be bigger than the concave function. Okay? And you have to recall just some standard facts of convex analysis. Hahn-Banach theorem is that a concave function is just the infimum of the affine functionals that are above it. Okay? So psi is the infimum of the phi that are bigger than psi. Okay? So somehow looking at functionals that are bigger than psi is just convex analysis of psi. Okay? And what I'm saying is that if you have such a measure, necessarily phi must be above, and if the two functions touch each other, okay, then, and if they touch, so there is a small difficulty that they have to touch each other, but not on the boundary of A+. Okay? So I don't know what happens when they touch in the boundary. And if they touch each other far away from the boundary, then you can build a measure. Okay? And once you realize that this is a good way of stating an extension in higher rank of these results, which are basically due to Patterson-Sullivan in rank 1, the construction is just their construction. And let me recall you that is in rank 1, you look for, beta conformal measure. Because the cocycle is scalar, so it's just all, you are fixing a cocycle, and phi is just multiplication by some number beta, okay? And the result is that if this exists, beta is bigger than the exponent of convergence, and for beta equal to the exponent of convergence, this exists. Okay? This is the existence is a construction of Patterson for a hyperbolic plane, and the construction was just extended directly by Sullivan, and this remark that the existence necessitates beta to be at least tau gamma was proved by Sullivan. And the reason Patterson-Sullivan introduced this in the beginning was to compute the Hausdorff dimension of limit sets. That is, since here it is a number, what you will compute here, what Patterson proved, and then it was extended, is that it was Patterson dimension 2, and Sullivan at least 2. Okay, for if gamma is in SON 1n, and is convex co-compact, then actually tau gamma is a Hausdorff dimension of the limit set. Okay, this is the origin that actually, in this case, this measure that you are constructing is just the Hausdorff measure on the limit set. So when you let the beta vary, at least tau gamma, what you are doing is changing the dimension in the Hausdorff measure. Okay, and you reach precisely, since if you have a measure, you prove that. Anyway, all this discussion is a discussion about Hausdorff dimensions in rank 1. Not in rank 1 in general, but in SO1n. Okay, so I have 5 minutes left, maybe, to discuss Bowen, Marguly, Sullivan. So I will come back to what I discussed here, the fact that what we want to discuss is the dynamics of the geodesic flow in rank 1, which is a flow in this space, okay? And actually we will discuss gamma invariant measure on G mod M, which is the same as discussing measures on that space. And what I told you is that this space has a product structure, so we are even luckier than people in hyperbolic dynamics in general, that it's not a local product structure, it's a global product structure. And this global product structure is called Hopf parametrization. And since I'm a mad group theorist, I will write it in a way that people from geometry will hate. So what is a Hopf decomposition in rank 1? What it tells you is that if you want to know, so you have your symmetric space in rank 1, and if you want to know geodesic, you have to know it's two endpoints. And we want to, this space, in rank 1, it is a unit tangent bundle. So if you want to know, if you know unit vector in the tangent bundle, then actually it is tangent to unique geodesic, because we are working as a universal cover. We are not working on gamma mod G mod M, but on G mod M. And the geodesics associated span by a unit vector is determined by its two endpoints. Okay, so what you are looking at here, what you are saying in rank 1, is the fact that you have a map from G mod AM towards G mod P cross G mod P. That is, if you take, because this data of those two endpoints, psi and eta, okay, it is the data of the unit tangent vector up to translation on the geodesic, which corresponds exactly to quotienting here, is this quotient by A, okay? So what it tells me is that I have a map from G mod AM to G mod P cross G mod P, and actually there is always a map of this form, because yesterday we discussed, and the range of this map in rank 1, the range is the set of psi eta, where psi is different from eta. Okay, but in higher rank, you still have this map. And we already studied it yesterday. As a range is the set of psi eta, such that which are in general position. So yesterday we discussed the fact that among flags, there is a unique, among pairs of flags, so group G admits a unique open orbit. Okay? And this is the flag that I define general position for flags in SLN, and maybe I did it also for a symplectic group, I don't remember. But again, this is a very explicit object for classical groups. And actually what happens is that if you look at the stabilizer of a pair of flags in general position, this stabilizer is exactly AM. So this is why you have this map, it's just the orbit map. Okay? And what I'm saying is that if I have defined I want to define a measure here on that space which will be invariant under A. But a measure, so a gamma, what I want to define is a gamma A invariant measure on G mod M. But this is what I mean by this is gamma invariant on the left and A invariant on the right. Okay? But this is the same as a gamma invariant measure on G mod AM. Okay? Just because I have a G mod AM is a quotient of G mod M by a proper action of A. Okay? And A invariant measures here is the same as measures on G mod AM. This is the same object. Okay? But now you see this space. It is a very big subspace of a product space, okay? And precisely, so I won't write statements because it's much too late, but what will happen is that due to the fact that I leave the other speakers do the work precisely, okay? We have defined measures on those sets, okay? And we will take product measures of two copies, so maybe it will not exactly be the same on the two copies in higher rank, okay? But what we can do, forget this is a technical difficulty, okay? So, and for special, certainly groups. So what we can do is take the product of two copies of the measure on G mod P cross G mod P, okay? And it turns out that this measure, if the group is nice enough, this measure will restrict to G mod AM on a measure here, okay? And this measure, you can lift it then to G mod M, and you get a measure on G mod M. And for the moment, this measure is not gamma invariant. And, but what happens is that there is a kind of miracle of group theory that has some explanations, is that here, the measure I'm building on G mod P, it's not gamma invariant, it will never be. It will be gamma quasi-invariant with a fixed cocycle. All this work we did was fixing the cocycle, okay? But when you look at the product, you have two copies of the measure. So when you look the sum, one cocycle here plus one cocycle here, and you restrict it to this guy, then actually this cocycle is a co-boundary. By a formula which does not depend on nothing, it's just a formula of the action of G, okay? Somehow, one explanation for this is that if you look at the K-invariant measure on G mod P already, okay? It is a formula that is it is a measure that is G quasi-invariant. But when you do this construction, if you start with a K-invariant measure, you end up with a measure on G mod AM, Okay? And on G mod AM, there is a G invariant measure. Because AM is unimodular, there is a reason why there is a G invariant measure. So you have a formula that takes the K invariant, the cocycle, the particular value of the cocycle coming from the K invariant measure, and that tells you that when restricted here, it is a coboundary. Okay? And it turns out that this formula, it always works. Okay? So yes, you have to prove this, okay? But it's a fact of geometry that this formula, when you start with twice the same cocycle here, you end up with a coboundary on this orbit. Okay? And when you do this operation, which don't have the time to do, okay, you end up with a gamma invariant measure on G mod AM. And this gamma invariant measure defines you a measure, an A invariant measure on this quotient, okay, and it's called the Bowen-Marguly. So in rank 1, okay, when you start with a Patterson-Sullivan measure coming exactly from tau gamma, okay, for the right exponent, okay, the measure you are constructing, it's called a gamma invariant, a Bowen-Marguly Sullivan measure. But if it is finite, it is uniquely defined. Okay? If it is finite, there is only one that works. Okay? And this is what's called a group of finite Bowen-Marguly Sullivan measure. And I will stop here. Thank you very much. This is my phone, sorry, forgot. Just on time to tell me that I should stop.
Coming in from the outside.
Someone does a question.
You said so there's a lot of gamma invariant measures on Gmod AM, right? But this one is somehow the most special one.
This is so if gamma is a lattice, is a Coulomb-Back lattice, this is a measure of maximal entropy. This is what you are trying to build is somehow. So it wasn't. I think this is the point of view of Sullivan. That is, Patterson was really interested in building the Hausdorff measure on the boundary. Okay, so because he wanted to estimate the Hausdorff dimension of the limit set, so he built this measure by this nice construction. But the spirit is that you're trying to imitate the construction of the Hausdorff measure, but in a nice way where you see the action of gamma. Okay. I think this is, I'm not in his mind, okay? But I think this is what you do. And then somehow Sullivan realized that you could do this product trick here by using the Hopf decomposition, and that the measure you would recover in case gamma is convex co-compact, it is a measure on the convex core of the manifold, which is the compact set, and there it's the maximal entropy measure of the geodesic flow. So what?
Does it depends on phi?
Yes, so here the measure fully depends in higher rank.
Which phi do you choose?
So so it is due. So it depends on what you want to do. You can choose the one you want. Thank you for this question. Here is a picture in higher rank. Okay, that in higher rank. Let me draw another convex picture. You have the limit cone. When you want to count, okay, you have the limit cone. On the limit cone, you have psi gamma. Okay, and then you want to count number of points in balls. Okay, so you want to count with respect, well, your expected exponent is the supremum of psi gamma x divided by the norm of x. Okay, so in the picture, what it means is that if you look, you have psi gamma, and here you have a convex function, which is tau gamma norm of x. Okay, and since the supremum is reached precisely for this value, it means that somehow this convex function must touch this concave one. Okay, but the norm, if you work with a Euclidean norm, the norm is a strictly convex function, which means that there is only one contact point. Okay, and at this one contact point, you can look at the tangent. Wow. So that is the tangent to the norm, which will be also, since you have contact, it will be also tangent to psi gamma. Okay, so if you want to count with respect to Euclidean norm, you use this phi. Okay.
The phi depends on gamma, or
it depends on gamma. The psi depends on gamma. Okay. Everything depends on gamma, okay? And it depends on the norm. That is, if you want to change the norm, if you want to count for some strange reason, you want to count with respect to another norm, you will get another phi.
Can it be related to the sum of the roots with some weights?
Not directly. So it can be written as the sum of roots with some weight because it's the basis of the space, but you don't know the weight.
Yeah, exactly.
Other questions?
Yeah. Who did the precise counting with this cluster psi and for what kind of group gamma?
So this technique was used by Sambarino. If you take gamma, I hope he's here. I didn't see him, so I hope I recite his results precisely. And you take gamma, which is a Hitchin representation. So he used the work of François Labourie and Olivier Guichard to say that if you take a Hitchin representation of a fundamental group of a surface, then you can prove that the cardinality of the set of gammas, such that the norm of kappa gamma, which is also the distance in the symmetric space, is smaller than A. This cardinality is equivalent as A goes to infinity to some constant depending on x exponential of A tau gamma.
And you proved this for Schottky groups?
I proved it for Schottky groups, yes.
Okay, any other questions?
So you said there is a unique direction, x, so that's why it coincides?
Because the norm, because I take a Euclidean norm, and Euclidean norm is strictly convex. So the picture is that, if you, for example, if gamma is a lattice, psi gamma is flat, it's a linear functional. Okay? So if you take a norm where you have some parts which are flat, you could have several directions. But whatever the psi gamma, you can show, whatever the group gamma, with respect to a strictly convex norm, you have a unique contact point. It's just convexity. Okay? But yes, and what happens is that for nice groups, that is another representation, psi gamma will be strictly concave. Okay.
And do we have information on this special direction that depends on the group, right?
No, because it depends also somehow. Yes, no. What kind of information?
Oh, is it continuous? So it should, does it give information on the group? It's kind of a mysterious direction.
It should be analytic, right?
It is
Just
analytic.
by
Does it-
Yes. Analytic. What do you mean? When you move the representation, when you move the
analytic.
yes. It should be because it's somehow all this business. When you have Anosov groups, etc., it can be translated inside the language of the thermodynamic formalism of the geodesic flow. And there, these are questions such as you have a family of potentials, which depends analytically, and you did ask whether their pressure depends analytically, these kind of questions. And these are questions that are solved, have been solved for a long time in the dynamical system community.
I think Andres will tell us more.
Yes,
about
Andres is
that.
a specialist.
He's the car, so.
Ask a good speaker.
Let's thank Jean-François again for being here.
Thank you.